very glad to see you back today. It means you feel you're doing good work, and I feel you're doing good work. Right. So today we're going to look at graphs, and we're looking at, once we look at graph, we're also going to look at equations. Now the first thing I want to do is right at the back of your study material. Yesterday we removed the first page at the back. It was the table, right? The periodic table. Now today remove the second last page, right? Because now it's got the information sheet for grade 11. Right. Now today we are going to look at equations and graphs, and that means that we are going to look at a lot of different topics, and you have to think about electricity at one moment, right? And the next moment we are going to be working with Newton's forces, and the next moment we are working with frictional force. So you really have to keep your thoughts together, right? Think about the topic we're working for, because we are going to apply the skills today. So we are going to move on right up to page 27. Everyone there to page 27? Okay, let's start off. If you look at physical science is looking at the universe and seeing what's happening and trying to explain that. And also something that is very important to us is to predict, right? We want to predict what's happening. Say, for instance, I change the temperature, right? And now I want to know what will the effect be. For instance, if you build a chemistry plant, right, you want to produce something. You build a big plant. You don't build that big building with lots of millions of rand and then you see if it works, right? You have to know before, and you have to know before. What will a change in temperature do to the product? What will a change in pressure do to the product? We want to think before we build it, right? We want to know before we start. So we do a lot of experiments, right? And in an experiment, you look at one thing that you change, right? There's one variable that you change, and then you measure one variable, right? What do we call the variable that we change? The independent one, right? We are independent, right? We decide, are we going to go 30 Kelvin, 60 Kelvin, 90 Kelvin? Are we going to increase with 30s, or are we going to increase with 2? We decide, we're independent, right? And then you get to the one that you measure. What do we call the one that you measure? The dependent, nice. Because it depends on what I choose. If I choose 30, 60, 90, it's going to be different from when I choose 50, 100, and 150, right? It depends on. Right, and then you get to actually the one that I think is the most important. And what is that? The other variables. Yes, nice. Constant variables, right. Because you can only look at two things. You can't change three things and then look at the final result, because you won't know which of those changed the final result, right? So all of today, I'm always going to ask you, which is the constant variable? Which is the constant variable? Because we want to look at only two at a time, right? So what we do is we do the experiments, right? And then we draw graphs from the data that we get, right? And then we look at that graph, and that graph is going to tell you what is the relationship between the two. So for instance, you look at this one. This is a straight line through the origin. If you get a straight line through the origin, we say they are directly proportional, right? Directly proportional. What does that mean? It means, say for instance, I look at this point. For a value x, I had a value y as my answer, right? So what am I going to do? If I go and I take x and I double the x value, I go to 2x, what will the y value be? It will also be double, right? So if the one increases by a factor of 2, then the other increases by a factor of 2 as well, right? Then we say they're directly proportional. Now, this is actually dangerous, because sometimes you say things are directly proportional when they're not directly proportional. Do you know about intermolecular forces and boiling point, right? If I have a bigger intermolecular force keeping my particles together, what's it going to do to my boiling point? It's higher, right. Is that directly proportional? No. Directly proportional would have been if the one doubled. If you doubled the strength of the force, then you would have doubled the boiling point. Is that true? No, not necessarily. It only means a higher boiling point is due to a bigger force. It is not with the same factor, right? It's only when the one increases with the same factor as the other one that we say they're directly proportional. So just be careful, right? More doesn't mean directly proportional. If this one doubles and that one doubles, then they are directly proportional. Right, but we'll come to that again. Okay, so what do we do? Now, let's look at gases. This is something that you did this year, right? Everything about gases. There are 4 variables that influence gas things, right? The pressure, the volume, the temperature, and the number of moles, right? If I have a container and I put in more moles of gas, what's going to happen? It's obviously going to change one of the others, right? So they all influence each other. Changing any one is going to change the others. So when you have 3 different laws that you look at, when you look at Boyle's law, Guy-Lussac's law, Charles' law, they can only look at 2 variables at one time. Say, for instance, you look at Boyle's law, right? Boyle decided to look at pressure and volume. Pressure and volume. So he did an experiment where he changed the pressure. Do you remember your Boyle apparatus? I hope you did that practical, right? You changed the pressure, right? You made the pressure bigger and you looked at what happened to the volume. And if you do that, if you change the pressure and volume, you have to keep the other 2 of the 4, you have to keep constant. So he looked at pressure. That's the one he changed. So it was the independent one, right? And then he measured the volume. So that was the dependent one. And then he had to keep the others constant. What's the others? Temperature, right? And also the number of moles. And how do you keep the number of moles constant? By having a closed container, right? So none of your moles will escape or you can't get extras. They are contained. So when you look at Boyle's law, don't be surprised if Boyle's law states at constant temperature, right? And also when there's the words enclosed gas. Because those 2 are only inversely proportional if you are with the constants, right? So let's look at this one. When he looked at P and V, he found them to be inversely proportional. So he did a lot of experiments. He changed the P, measured the V, and then he went and he drew the graph from that results, and he got this. And this told him that it is inversely proportional, right? Do we like graphs like that in the lab? No. You can't work out gradients. It's difficult to read from the graph. So what do we do when we get a graph that is inversely proportional? That is a hyperbola. What do we do with that? Well, we go and we change one of the axes, right? So you take all your p-values in your table and work out 1 over p, 1 over p, 1 over p, and then you go and plot it again. And then you get a straight line, right? To who's this news? You are very quiet today. Do you know this already? I hope so, right. Okay, and then Guy-Lussac and Charles, there's 2 other laws. Charles, for instance, looked at temperature and volume, right. When he looked at temperature and volume, what did he have to do? Keep constant. He looked at those 2, so he had to keep constant pressure and the number of moles. How do you keep the number of moles constant? Enclosing the gas, right. And now, here's something nice. How did he keep the pressure constant? What did he do in his experiment in order to keep the pressure constant? He put the gas into a syringe, right? A syringe with a plunger that can move out and in, right? Now, if you leave that plunger to do what it liked to do, right? And it stopped, what is pushing on the outside of the plunger? Right? On the outside of the syringe, what is pushing? The air, 1 atmosphere, right? So if it is not moving, what is the pressure inside? also 1 atmosphere, right? So we start off with 1 atmosphere and 1 atmosphere. Now he takes the syringe and he puts it into hot water. Right, thought experiment. I'm putting it into hot water. What is going to happen? If it goes into hot water, what will happen? That plunger will move, right? Do you expect it to move in or out? Hot water? Out, right. And it will move and then it will stop. Why does it stop? It will stop once the pressure outside and the pressure inside is the same. So he was able to keep the pressure constant by just waiting, right? If he waited until the plunger moved to where it wanted to move, then he knew the pressure outside and inside is the same once again, right? So that was a nice way to keep it constant. And then when he went to draw the graph, when he did that, and he had his values in Celsius, the graph looked like this. It's not a graph through the origin, right? So if it's not through the origin, then it's not directly proportional, right? You have a plus y-axis something, right? Not directly proportional. And do we like that? No, we didn't like that. So what do? We change the values, right, to Kelvin. Because once you do it in Kelvin, then it goes through the origin, and then it is directly proportional, right? So if you learn Charles's law, then you don't just say volume and temperature are directly proportional. You say volume and Kelvin temperature are directly proportional. It is not true for temperature in Celsius. It's only true for Kelvin, right? And that is where we got that. So this is just one example, yes?
The line goes to the origin. Is it not just theoretical? Because gases have matters to occupy space.
Yes?
The volume.
Yes, yes. We are going to talk about extrapolating and interpolating. Sometimes you have values, right? And then you want to know what's happening to this side and that side. So it's actually true. It can't go down to. But we extrapolate. We draw the line longer, right? We'll get to that once we do the discussion on how to analyze graphs as well. So then ask me again if it is not clear at that time. Okay, right. But yes, you will never quite get the volume. So this was just this last part. We extrapolated. We drew the line on. You can make that in a small, just dot, 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 if you want to. Right. Okay. So what are we going to do with this? Now, the first thing is, can you turn to page 30, please? Now, when you draw the graph, we are going to use the graph to get the relationship, right? If it was a straight line, and the important thing is through the origin, right? If it's a straight line and it's through the origin, then I will say they are directly proportional, right? So this is the experiment was done, and from that experiment, they derived the equation. What are we going to do? We are going to stand on the shoulders of giants. Eh? That was what Newton said. He is standing on the shoulders of giants because a lot of people already did the practical, right? They already did a lot of experiments and they already got the equation from that experiment, right? So now we have the answers sort of in equation form. So sometimes we are going to start here and we're going to work back. For instance, I can ask you to draw a graph of the net force on an object versus acceleration. Now, the first thing is, when we say versus, what do we mean? We always mean you start off with the y-axis, right? And then versus x-axis. So it's always y first and then x, right? So if they say net force versus acceleration, then net force must be this one, acceleration must be that one. Everyone happy? Okay, but if I look at that equation, right, I want to draw F net and A. And I can only draw F against A if the other one is constant, right? So I always have to check, is the other one constant, right? So why can I say m is constant? Because I'm working with an object, right? An object. The moment that they tell they're working with an object, I will say, okay, so m is a constant. It's not changing, right? So for this one, F net equals m times a, m is a constant, so if a doubles, then that right side doubles, and therefore the left side must double, right? So they are directly proportional, and it looks like this. Right, next one. Do you remember about refraction, eh? Right, the refractive index was the speed of light, and what is c? It's in a vacuum, hey? It was the speed in a vacuum, right? And v was the speed in a specific medium, right? Now, what can you tell me about the speed of light in a vacuum? Nice one, yes, constant, constant. It is constant, and it also, you even know it's 3 times 10 to the 8 meters per second, right? Sorry for that writing. Okay, so c is a constant, right? And once you know that one is a constant, what is the relationship between the index and the velocity of the speed of the light in the medium? They are inversely proportional, right? So now when you draw n and v, you get a hyperbola because they're inversely proportional, right? Now, let's say they didn't ask us for n and v. We don't like hyperbola, so what will we do more often? We will more often draw n against 1 over v, right? The inverse of v. Because if you have the inverse there, you will say this axis is directly proportional to, and now that is in the axis, and you will end up with a straight line, right? Or you could even have it 1 over n against v. That would have been the same. Right, this should not be new, right? Next one, directly proportional to the square, right? Say, for instance, kinetic energy of an object versus the velocity at which it moves. Same thing, an object, what does that tell you? That m is a constant here, right? So if I look at Ek equals half mv squared, half is already a constant, right? And m is also a constant. So you can leave that out, and Ek will be directly proportional to v squared. So if you draw Ek and v, square will tell you with an parabola, right? It's squared. So you end up with a parabola. What could they have asked us different? They could have asked Ek versus v squared. What should that one look like? Now it's a straight line, yes. Because now the square is in the axis, right? So then it would have been a straight line. Okay, very last one there. If you look at Newton's universal gravitational law, right? Now I'm asking you, draw the force of attraction between the two objects versus the distance between their centers. So we're looking at F and we're looking at R, right? What do you know? Well, we're in the same universe all during the experiment, so G is a constant, right? And they're talking about objects, right? 2 objects. So the masses is also constant. So you end up with F being directly proportional to 1 over R squared, right? And that gives you a graph. Now, this one is, you know, hyperbola, right? The hyperbola was that one. The one in red now is the hyperbola, right? So if the R was squared, what did it look like? I always say it's just tilted a little bit, right? Can you see that one? That is for the squared one, right? Okay, it's tilted a little bit to the side. This is a difficult one. I haven't seen them really ask this, right? But what will you get when you draw F against 1 over R squared? What should that one look like? Yes, nice one. Now it's a straight line, right? Okay, just 2 more. And actually the last one is for grade 12. So we'll leave that a little bit. Let's look at this one. Right, they are talking about gravitational acceleration, right? Do you have this equation on your information sheet? It shouldn't be there, right? No, it's not there. if you have to use this one, it's one of those that you have to derive before you can do anything with that. Right. So where does it come from? It comes from the universal law, G M over R squared, right? I'm now using a small n and a big M, because I'm going to say big M is the Earth and small m is little me. Okay, right. So if that is the force between the Earth and you, what do we also call that force? It's your weight, eh? It's your weight. So you can replace that with mg. Right, that's another way to calculate your weight. So this is a way to calculate your weight, that is a way to calculate. They can be the same. And then if you look at it, you will see small m. Who's small m? You. On both sides, right? On both sides. So that can cancel out. And then you end up with g being gm, and never mind if it's in front or up top, same thing, right? Over r squared. Now, what can we see from this equation? Right. The gravitational acceleration. Is there a small m on that side? No. So does it depend on your mass? No. Objects with big mass, objects with small mass will have the same gravitational acceleration, right? So if there's no air friction keeping you, right, it's just gravitational force, then all objects will travel, and on Earth that is 9,8, right, meters per second squared. Because the mass of the Earth doesn't change for big and small things. The radius of the Earth doesn't change for big and small things, right? And it doesn't depend on the mass of the small thing, right, on the thing that's falling. Right, so if you look at the graph, and they ask G and different masses, then G doesn't change. It's 9,8. It doesn't matter if the mass is 2 or 4 or 6 or 8 or 10 kilograms. It's all falling down at 9,8 meters per second squared. Right. So if you look at your equation, then you will see, I think the big G is missing there. Hey? Right. Everything there at the top is constant. Right. So then you get, and then next year when we get to acids and bases, you will also use the pH graph, because then we look at the log graph. But now we're going to just skip that one to start with. Okay, so this is how they derive the equations, right? Or how we are going to go from equations to graphs. Turn just back to page 28 now. Right. So the one thing we want to do is we're going to draw graphs just after this. Right. The other thing you want to do is we want to predict, right? If this change, what's going to happen to that one? Now, very important, you can only predict if all the other constants are constant, right? Only one thing changing. Or you have to look at everything that's changing. So let's just look at this example, right? They tell you you've got sphere A with a mass of m, right? And you've got sphere B with a mass of 2m. And they attract each other with a force F, right? And now they ask you, how will the magnitude of the force change if the mass of B is doubled? So only one mass will be doubled. Right. Now when we do that, we start off with before the change, right? We start off and we say, okay, let's look. Before the change. Before the change, you would have worked out F with Gmm over R squared, right? Now I'm changing something. What's changing? Now I've got a new F. Did big G change? No, you didn't leave our universe, right? So the universal constant is constant. Did small m change? No, they said nothing about it, the one, right? They changed the other one. So it doesn't matter if it's M1 or M2, but one of them has doubled, right? Anything about the radius, the distance between the centers? Nothing. So we take that as staying constant, right? And then you say, okay, I now have this, but I want to compare that to the previous one, right? So take out everything that's strange, so that we will go back to F. F used to be Gmm over R squared. So go back to Gmm over R squared, right? because that was what was F before, right? So now we have 2 times the original F, right? Twice. Okay. Another way to do the same thing would be to look at the relationships first, right? To say, okay, that is directly proportional to that because all the other things are constant. And then saying, if this one doubles, then obviously that one will double as well, right? Okay, I think we don't even have to look at the second one. I think you are ready to look at the first one on the next page. Page number 6, number 1, 6-1. Right. See if you can decide which multiple choice answer is the correct one. Right, so the question said 2 asteroids are 100 kilometers from each other and experience a force F. That should tell you what we're working with, eh? It's the universal rule once again. So I'm looking at F equals GMM over R squared, right, or 1 or 2 if you want to. Okay, and now they say if the 2 asteroids move to a position 2,000 kilometers. Now, I did not put the 1,000 in there, right? I just want to look what's happening to it. So don't put numbers in there. Just put the R in there and say, okay, how's it going? Now we have a new F. Right. What changed? Did the constant change? No. Constant's the same. Did the mass change? No. It's still the same 2 asteroids, right? So M1 and M2, same as before. What changed? We used to be 1,000 away, so that R was 1,000, right? And what do I have to put in now? 2,000, right? So it is twice the R that I put in on this side, right? And then you just have to remember that it's squared, right? Okay. So I want to go back to this one, right? This one is my F. So everything that's not in there, move it to the front. What's moving to the front? At the top, we're fine. At the bottom, 2 squared is 4. So I get 1 over 4, and the rest is just, once again, G M1 M2 over R squared. So now, there I'm back to the old F. Right. I took everything strange out. So it's 1/4 of the force before. Right. You should have had things like this in your exams, right, and your tests. Okay, next one. See if you can find 6.2. And if you finished with 6.2, go on. Go on.
Doesn't give any answers.
Okay. If you work them out, one of them is the same as that. Which one?
4.
Perfect. Right, so it's once again the universal law, right? F equals G M1 M2 over R squared, and that they call W, right? So we start on Earth, right? And now we're going to this other planet. If we go to the other planet, now we're on Mars, right? Same universe, same G, right? Did the hammer change? No, so one of the M's should be the same as before. The hammer didn't change. Now we're on Mars, and what do you know about Mars? It's 1/10 right? 1/10 of what we used to have as the mass of Earth, right? And then you look at R. Mars has a radius of half the Earth's radius, so R over 2. And remember to square, right? Now, what do I remove at the top? 1 over 10, right? What do I remove at the bottom? Half, but it's squared, 1 over 4. And the rest is just G M1 M2 over R squared, right? Now, what do you do when you divide by a fraction? Multiply by the inverse, and then you end up with 4 over 10, right? And the rest is just what we used to have as the force, which is W, right? So it's replace, and then look at it and see if you can make it into a neater fraction there. Right, next one. 2-point charges. See if you can do number 6.3. If you finish with 6.3, go on 6.4. What was the most important words in this question? Word. By. Right? It reduced by 3 millimeters. So it doesn't end up being 3. It used to be 4 millimeters from each other. And now I reduced the distance by 3. That means I end up with a 1 millimeter distance. Right? So, 2-point charges, whose law? Coulomb's law. Okay, so we're starting with F equals K Q1 Q2 over R squared, right? Nice. Now we change it. So now we have a new F. The constant obviously is constant, right? Did they change the charges? No. So Q1 and Q2 just go where they used to. Right. And what happened to R? What did we put in there before? That used to be 4 millimeters, right? And now we only want to put in 1. So I'm putting in 1/4 of what I used to put in, right? Okay, and if you squared that, you end up with 1 over 16 times the old F. And 1 divided by 1/16, if you divide by a fraction, you're actually multiplying by the inverse, right? So you end up with 16F. And that's why the answer was E, 16F. So sometimes it's understanding and sometimes it's math that's the problem. Hey, everyone happy with 16? Right. Now, go on to number 4 and see if you can find the answers for us there. Number 4. Right, finished, 6.4. Right. Now, for those guys who are not that happy yet with electricity and power and things like that, if I look at 2 bulbs and they ask me about brighter, tell me what should I look like at to decide if it's glowing brighter or not? Which variable is going to tell me about brighter? I hear about resistance. Someone who don't say resistance? Come on, what does bright mean? Okay, let's go one back. How do you observe light? You observe light by photons of light hitting your retina. Is that right? Okay. So it's the energy that is reaching your eyes that is interpreted by your brain as light, right? So if you have a brighter light, that means more energy is reaching your eyes. If you look at a lamp, right? Brightness is all about power, right? Give me an equation for power. If you look at your information sheets, right? Power, there's a lot of wind. Let's look at the first one. P equals W over delta T. What does that mean? If I have a 300 watt lamp, it means that 300 joules of electrical energy received by the lamp is converted to light energy per second, right? So if you have a bigger power, yeah, what do we measure power in? Watts, right? If you have more watts, if you have bigger power, then you will have more energy released every second, right? So the power is actually the brightness, right? If there's more light energy released, then it will look brighter to me, right? Because more energy will reach me, right? So it's all about power. Now we have a small problem. When you were in grade 10, your teachers told you to look at current, right? They told you something like, I have two identical bulbs in a circuit, right? And then they asked us, is it identical bulbs? Which one will have the brighter? Let's put another one in parallel here. Make it interesting. A, B, and C, right? If they told you this was identical bulbs, what did you look at? You looked at current, right? You looked to see who's got the bigger current. And then you would have said, A is brighter than B and C. Is that right? But that was when it was limited to things that are identical. Let's go back. If it's not identical, can you see R also influence the power, right? There's an R, there's an R. The power is not only influenced by current. So when you were in grade 10, if you looked at P equals I squared R, if R was kept constant in grade 10, then it was fine to say the one with the bigger current will be the one with the bigger power. That was fine, right? But now you're not in grade 9 and in 10 anymore. What are we going to do? We're going to change everything, right? We're not going to tell you they're identical. So in this question, what do I tell you? I tell you one has got a resistance R and the other has got a resistance 2R. So now I'm changing R. So immediately you can't just look at I, right? You can't just look at the current. You have to look at the power, right? So for brighter, you use who's got the bigger power. That's the question, right? Who's got the bigger power? Now let's look at them. When they are in series, we now want to look at power, and we also want to say who's got the bigger power for a different R. So we're changing R, right? We want to know what's happening with P, R and P. So it's either that equation or that one, right? Which one should I choose? They both tell me something. The one tells me a bigger R will have a smaller P, and the other one tells me bigger R, bigger P. So which one is correct? They're both correct. It depends on the constant. So let's go back. If they are in series, what is constant? What is the same for bulbs that are in series? Nice. So if they are in series, then current is my constant, right? So which equation will I use now? Now I use P equals I squared R, because now I know current is constant. And the moment that current is constant, what is the relationship between the power dissipated by this lamp and the resistance? They are directly proportional, right? They're directly proportional. What does that tell you? The bigger resistance will have the bigger power, will be brighter. Right, so 2R is now going to be brighter. Right, let's look at parallel. Parallel. Once again, I'm changing resistance, so I have to have R in my equation. I'm asking what's happening with power, so I have to have P. But what do we know about things that are in parallel? Same potential difference. Yes, I can hear you. So V is my constant when they are in parallel. Right, so go back to your information sheet. I want to look at P and R, so they should be in the equation. And I'm going to choose the bottom one because then I can say V is constant. Right, so now I'm saying P equals V squared over R, and that one is constant. So if they are in parallel, what's the relationship between P and R? Inversely proportional. Right, inversely proportional. So which one will be glowing brighter? So now R will be brighter. Smaller resistance, bigger power, more energy per second, more light, brighter. Are you happy? So can you see how very important is the constants, right? You have to be able to talk about the other things, not just about the two that you are looking at. You really have to be able to talk about the others. So let's look at that one. Okay, number 6.5 down there. You've got P and Q, they're two isolated spheres. They exert a force F on each other, and now they tell you the spheres are brought in contact and replaced at a distance that is double. So they are in contact and they are at a distance that is double the original. Right. And now they say determine the force between the spheres after the contact, right? But in terms of F. Right. So you have to say so many times the old force. Right. Let me leave you with that. Do that quickly. Right, which equation? Coulomb's equation, right. F equals K Q1 Q2 over R squared. We're working with two charges, right. So this is the old one, right? And now I want to know what will be the new one. So obviously K is a constant, so that's fine, just put it in there. Now, our problem is what happens to the charges? Now, what did they do? They brought them into contact, right. So let's start off. This one was a -2 microcoulomb, and this one was a +6 microcoulombs. Allowed to touch, and then once again removed from each other. How do I get the new charge here? Yes, I'm going to add them together, right? So Q new should be Q1 plus Q2 over over 2, right? And now we talk about the algebraic sum, hey? Because this is the only place in static electricity that you put the plus and minus in, right? You don't put the plus and minus in there, but over here we have to say it is a -2 microcoulomb added to plus 6 microgram divided by 2. That will give you plus 4 divided by plus 2. So they end up plus 2 and plus 2 microcoulomb. Happy? So now we can say, what did we use to put into Q1 as its value before? Before we used to put in there 2, right? Remember the minus was never there, right? It was just 2. What are we now going to put there? Still 2. So the same as before, right? Now we look at the other one, Q2. We used to put in 6. What are we now going to put in? 2. So we're now putting in 1/3 of what we used to put in, right? It used to be 6, now it's 2. It's 1/3. You've divided by 3, right? And now we look at R, and they told us double the distance. So you have 2R, and just remember the square. Right? Okay, time to take all the strange things to the front. What's strange at the top? 1/3, right? What's strange at the bottom? 4. And the rest is just K, Q1, Q2 over R squared. So fine, that is the old F. 1/3 divided by 4, 1/12. Happy? Good. Now I think you are ready to draw some graphs. So let's move on, let's move on. You should move right onto page 33. Page 33. Right, let's do the first one together, right? You have to draw a sketch graph, so you don't have to put numbers in there, right? Just a sketch graph of the acceleration of an object versus the net force. So which one should be on the y-axis? The acceleration, right? It's y versus x-axis, right? So acceleration over there and net force over there, right? But one of the marks for drawing a graph, usually they want you to write a nice heading, right? And then the second mark is for what? You have to label that, but you also have to add the unit. If you don't add the unit, you don't get that mark, right? So it's both label with variable and unit, right? So at least now I have one mark, right? So now we want to draw the graph, right? We're talking about acceleration, we're talking about net force, right? And there's something extra, something you have to read between the lines. What does an object tell me? It tells me m is a constant, right? I'm working with the same object always, so m is a constant. So when I look at that, F net equals m times a, and m is my constant. So what is the relationship between a and F net? Directly proportional, and therefore it should be a straight line through the origin. Right, go on with the next one. See if you are comfortable with that one. So they asked about power versus potential energy. So power should be this one, potential difference should be on that one. Power in what? Potential difference in volt. Right, I've at least got the first mark. Okay. And now they're talking about, and what does the resistor or a resistor tell you? That tells you that R is now my constant. Right, so R is my constant. Go back to your information sheet. Which equation? I'm looking for power equations, and I need to have an R, or I may have an R. I definitely need a V. Right, so now I'm with that one. So P equals V squared over R. Right, and R is now my constant. If R is my constant, what is the relationship between P and V? It's directly proportional to the square. Okay, so what should the graph look like? It should be parabola. Right. For the guys who's lost, turn back to page 30. Right. When you get directly proportional to the squared, then you end up with a parabola. Right. So it should look like that. Okay. Next one. Oh, sorry. Unfortunately, I see we've done this already. Hey? They're asking for the gravitational acceleration of an object, right, on the Earth's surface versus the mass of the object. Right. If we look at G, it was that one that we had to derive, right? You have to derive that one. And we said G and M and R, they are all constant. The big M is the Earth's mass. That is not changing when you take different objects, right? G is in any case a constant. The radius of the Earth is a constant. So everything there is a constant. So G is independent of the mass. So G in meters per second squared, mass kilograms, it's 9,8, 9,8, 9,8. Doesn't matter what the mass is. Huh? The mass can be anything. This will still be 9,8. Right, go on with the next one, number 4. And if you finished 4, go on to 5. Right, let's look at number 4. They ask you to draw a sketch graph of energy dissipated by a 30-watt lamp versus the time. So we have to have energy on the y-axis, and we have to have time, on the y, and time on the x-axis, right? And the fact that they tell a 30-watt lamp, the moment that they tell you, then the power is fixed, right? That power is fixed. So now, if we look at that one, give me an equation with all of those. You get P equals W over delta T, right? And we want to draw W and delta T. They've already told us that P is a constant. So what is the relationship between V and delta T? They are directly proportional. Right, if you've got a problem with the maths, you can prefer to write that one to take the delta T to the other side, right? P times delta T equals W. And then it's easy to see if this one is constant, those two are directly proportional, right? Directly proportional. Okay, so what does that mean? Straight line through the origin, right? Straight line through the origin. Okay, next one. Kinetic friction, right? So we're looking for kinetic friction of objects versus their masses. Okay, so you have kinetic friction over there. That will be in newtons. Mass in kilograms, pulled across the table with the same force. So you have something, you're pulling it with some force, right? Okay, and they're asking about friction. Now, we have a problem. Do you have an equation with, sorry, not static, kinetic. Do you have a equation with kinetic energy and m in the same equation? No, we have for kinetic, you have mu k n, right? Okay, but do you have an equation for n that has got m in? What is n? Well, if it's only horizontal forces, this would have been gravity, the same, hey? The gravity downwards would have been even to the normal force upwards. And what is Fg? That is actually m times g, right? So now we had to combine two equations to give us one that's got all the things that we want to look at. Okay, so what's constant? A table. What does a table tell you? They're pulling, the m over there is the thing that they are pulling, and they're pulling different objects, right? But mu, right? If it's a table, what does mu determine? When do you have a big mu? When do you have a small mu? If it's the same table, it's the same smoothness, right, all through. So mu is a constant, right? Mu is a constant. And g is also a constant, right? We're staying on the same world, right? Same earth, right? So if both those are constant, the mu k and g is constant, then Fk is directly proportional to the mass. So the mass is bigger. So the bigger the mass, the bigger the gravitational force, the bigger the normal force, the bigger the frictional force, right? And they ask things like this. They ask you, if they increase the mass of the object that's being pulled, what's going to happen to the frictional force? And you can feel it, huh? It's going to be bigger friction. There was a question over there. Did I answer your question? Yes, perfect. Everyone happy? So sometimes there's not one equation that can give us the answer. Then we might have to substitute another one in there. Right, let's look at the next one. They want the power dissipated in a resistor. What does a resistor tell you? Now we're looking at an R that is constant. It's always the same resistor they're using, right? So R is a constant, and that is versus current. So the other one is I. Okay, draw that one. Yeah, but they ask you to draw to I. They didn't ask you to draw to square, so you have to have the parallel. But if they ask you to draw square, then it would have been a straight line, because then the two axes are directly proportional. Right, so did you choose an equation? Right. R is constant. We're looking at P and I. We need an equation with P and I and R. So it should be P equals I squared R, and R is my constant. Right, so immediately P is directly proportional to I squared. So if I want to draw P and I, P measured in what? Okay, and I in amps, right? Okay, so what should that look like? That should look like a parabola, right? If it's squared, then it's parabola. Right, if I ask you to draw P versus I squared, what should that one have looked like? That one should have been a straight line, right? But if they ask me just I, then that one should show the square, right? Okay, next one. We've done that already. Okay, refractive index, n, right? We're looking for n of a medium versus the speed of light, v. We said n equals c over v, right? The refractive index is the speed of light in a vacuum, right? And that is my constant, right? And then n is inversely proportional to v. So this is n. What is the unit of n? Nothing. So that's a perfect answer if you give nothing, right? Against v, right, versus v. And v is a velocity, so that should be speed meters per second. Right, so inverse, what type of graph am I looking at? Hyperbola, yes, hyperbola. Right, I don't like that graph. I would have preferred n against 1 over v. What should that one look like? Straight line through the origin. Perfect. Nice. Right, you did electromagnetism, right? So go on with the next one. I'm sure it's not a problem to get to the relationship. Sometimes it's a problem to get to the correct variables. Hey. Magnetic flux. What is the symbol for magnetic flux? Phi. We have to speak some Greek, eh? To some people, all science is Greek, but to us, just phi is Greek, right? And what do we measure phi in? What is the unit of phi? Now, I always tell my learners, if you have problems, just take it apart, right? You've got that nice circle. Just pull out that and make it little sticks, and then you'll see it's a Weber briar. Hey. Do you know a Weber briar? Right? Big black thing with 3 legs. They call it a Weber. No, never mind. Right. This we measure in Weber. Right. So, I have my flux, and I'm going to measure it in Weber. And that is versus the strength of the magnetic field. Right. What's the symbol? B. B. What do you use E for? Electric field, right. Electrostatic field, right. B. And what do we measure it in? Tesla. Nice. Tesla. Right. So this is magnetic field strength in Tesla. Right, and now for those guys who can't remember, fortunately, the Department of Education issue you with a nice information sheet. Right, so there it is. Phi equals BA cos theta. Phi equals BA cos theta. Right, now what is constant? Now they're talking about a coil, right? A coil. So what can you assume is constant of that coil? You can assume A is definitely constant, right? And if we're looking at the same, I'm also going to take cos theta as constant because they didn't tell us anything about turning, right? So we assume we're looking at the same coil in the same turning as before. So now my constant is A cos theta is my constant. And what is the relationship between the flux and the magnetic field? Directly proportional, right? So this should be straight line through the origin, right? Straight line through the origin. Right, so next year you're going to do still more equations. And it doesn't matter, you can do any equation. You just have to make sure that all the things you don't want to look at is constant, right? So determine which variables you want, and then choose an equation where the rest is all constant, right? Okay, so now we can draw graphs, or we can use graphs to get the relationship, right? What can you do with a graph to get information from that graph? Now, if you go back, go on to page 34. Right, there on page 34, we're going to look at 3 techniques of how can I get information from a graph. Now, the very first thing is just reading from the graph, right? Say, for instance, they gave you a graph and they told you this is current. I've got a circuit and I'm changing the current every few seconds, and I have a current like that, and it's 5 and 10 and let's say 2, and that's 3 seconds, and that is 8 seconds. Okay, so they give me a graph, right? And now they ask me, what is the current at time 5 seconds? What is the graph? What is the current at time 5 seconds? What are you going to do? What's the answer? You're going to read it from the graph, right? If they ask you one of the axes, then it's reading, right? So you just say, okay, 5 seconds, it's around about there, then I go up, and my graph value at that one is 10. So it's 10 ampere, right? Or they could have asked the other way. They can ask you for what period of time, right, is the current at 5 amps? For what period of the time is current at 5? And then you say from 0 to 3 seconds, right? So if they give you a current time graph and they ask either current or time, then it's just reading off the graph, right? So this is the first technique that you can use to get information from a graph. Just read it, right? Now we get to the second one. The second is the gradient of a graph, right? The gradient of a graph. Now, how do you get the gradient of the graph? If you work out gradient, it's always y-axis divided by x-axis. Is it right? Y divided by x-axis. So let's say we had f net equals m times a, and m was my constant because I was using the same object. Then f net was directly proportional to a. And if I draw f net versus a, right, that would have been a straight line. What is the gradient of that line? Now, if we work out gradient, that will be change in the y-axis. So that is something f of f net, right, divided by something a, right? So it's y-axis, which is f, divided by x-axis, which is a. What is f divided by a? Go back to my equation. F net divided by a should be m. So now the gradient is m. Everyone happy? Okay, but if I ask you to draw a versus f net, you would have done the same. F net equals m times a. M is my constant. So therefore, f net is directly proportional to a, or a is directly proportional, same thing. And therefore, straight line through the origin. But this time, what is represented by the gradient? Now, if I look at the gradient should be change in y-axis over change in x-axis. Is that right? So now, what is A over F net? A over F net should be equal to A over F net, taking M over to the other side. Sorry. That was nearly a math mistake on my part. Did everyone get 1 over M on the other side? Right. If you want the F down there, right, you just divide by F net on both sides, then you get it on the other side at the bottom. Right. But how do you get M to the other side? By dividing by M over here and dividing by M over there. Right. So what's the gradient this time? 1 over M. Right. So sometimes when we start out with graphs, especially in grade 10, when you do Ohm's law, we start out and we say, okay, we draw F against I, and you get that, and the teacher tells you, okay, so this is a straight line, right? So it's just got one gradient. A straight line has just got one gradient, right? So the gradient is the constant thing. What's constant? Constant in Ohm's law was the resistor you were using, right? And that's how they start off to show you gradient is R, right? But if you drew the axis the other way around, it would have been 1 over R, right? So we used to ask you the easy things, but we're now moving on to more difficult things. So sometimes we're going to do it the other way. Let's just turn back to those that you've already drawn on page 33. Right. Now, if you look on page 33 at number 4, right, we got that straight line for energy versus time. Now I want you to tell me, what is the gradient of that one? The gradient of that one will be y-axis divide by x-axis, right? And fortunately, that is exactly our definition of P. So this time, that gradient is my power, right? And that will actually be 30. So I already know the gradient is 30, right? Let's go on. The next one. The next one, we also had a straight line, right? So my equation was Fk equals mu k mg, right? How do I get the gradient? Gradient should be change in y-axis over change in x-axis, right? So how in this one can I get Fk over m? That will be mu k times g. So the gradient is mu k times g, right? So they can give you the graph and tell you you're on Earth, then you have g, and ask you to get mu from the graph. So then you say, oh, the gradient is mu times g, and g is 9,8. So work out the gradient with values on the line, right? Work out the gradient, and that will be mu times g, and you already know what's g, then you can get mu. Right. Okay, let's go on. So that is for gradient. So whenever you need the gradient, it's y divided by x. Now the very last one you can do is you can get the area under the graph, right? The area under the graph. How do you get area under the graph? Now I gave you an IT graph. Let's just quickly think about an easier IT graph. If the IT graph, IT seconds area, if the IT looked like that and it was 3, and I told you, okay, let's look at this for, say, 6 seconds, right? It was an ordinary question. I asked you, what is the current, what is the amount of charge that passes a point when the current is 3 amps and it's flowing for 6 seconds? Now, what is the symbol for charge? Q, right? Q equals I delta T, right? So, if you look at Q equals I delta T, now, there, nothing was kept constant, right? They chose to have the current like this. Now they're asking us from there, work out how much charge passed. The charge that passed would have been 3 amps for 6 seconds, giving you 18 coulombs, right? Can you see that is just the area under the graph, right? That would have been 3 times 6 as well, right? Now we get to a graph where I is changing. Now you've got a problem, right? What do you put into your equation? Which I do you put in there? You can't, right? So actually you have to go to first year mathematics, right, and start integrating and so on. So at the moment I can't. What do I know? I know the area down there was I times delta t. So now I don't have a constant value, but I can still work out the area, right? So that's what we're going to do. If you look at the area under the graph, it is the two multiplied by each other. So the area will be something I times something t. And I times t is your charge q. So now you have the amount of charge that's passing is that area. The same as over here, right? But here it was easy to do it either way with area, sorry. Right, we'll be back shortly. Right, okay. So what is the three techniques that I can use? I can either use reading from the graph, right? I can get the gradient of the graph. What do I do with gradient? It's y divided by x and see with my equation what it gives me, right? Or I can work with, still not there. Okay, or I can work with the area under the graph, which is a multiplication of the two, right? Now, if you turn to page 35, right, up there on 35, we're going to look at the first one there. Okay, I think it won't be normal just now, sorry. Right, let's zoom in. Right, so we're looking at this one. Plastic containers with different masses are pulled over a surface A, and then they get graph A, right? And then pulled over another surface, surface B, right? And now they say a graph was constructed of the kinetic friction on the containers and the normal force acting on the container. So you've got kinetic, sorry, there's an S, it should be a K, hey? Kinetic friction against normal force. Right, so start off by telling me which equation. Fk equals mu k n, right, Fk mu k n. Right, so it's that equation. And they draw one graph for A, right? So that is one surface. And obviously if it's got one surface, surface A has got a mu k of its own, right? So mu k all over surface A, mu k will be the same constant. As you draw it along, it's the same, right? But now they take things with different masses, so they've got different n. What is the relationship between the kinetic energy and kinetic friction and normal force? Directly proportional, right? So it makes sense that it's a straight line, right? What is the gradient of that line? The gradient of that line should be Fk divided by n. What is that? That is mu k, right? So the gradient of the line tells me about the friction coefficient, right? So if you look at the two lines, who's got the bigger gradient? A, right? So A has got a bigger gradient. That tells me that A has got the bigger frictional coefficient. And if the coefficient is bigger, what does it tell me? It tells me A is less smooth, right? Rougher, a rougher surface, right? It's less smooth, therefore a bigger mu, therefore a bigger gradient. And you see how we use that? Right. Okay. But obviously if you just thought about it, you might have got it another way around. It's just nice if you can use the gradient because then you can use the correct terminology, right? Okay, let's go on to the next one. Next one, an isolated sphere is negatively charged by adding extra electrons to the sphere, right? So it used to be negative, and now they're putting extra electrons on that. Right, so what's happening to the charge? It used to be 0. If I put extra electrons on there, now it's going to become charged. Right. And how do I calculate the number of electrons? Do you have an equation for number of electrons? Yes, I think it's on your information sheet. At least it's on the grade 10 one. Nope, you have to learn it. What is that equation? N equals Q over QE. Right. What is QE? The charge of 1 electron. Right. It's 1.6 times 10 to the minus 19. Right. So that's a constant. Right. So what is the relationship between the number of electrons that you put onto the sphere and the charge? That's directly proportional, right? Directly proportional. That's why you get a straight line, right? And now they ask you, what does the gradient of this graph represent? Okay, so gradient. Gradient being change in y-axis divided by change in x-axis. What is Q over N? My equation used to be N equals Q over QE. So how do I get Q over N? That will be equal to QE. Right, so what is represented by this gradient? Yes, the charge of 1 electron. And you can even give the 10 to the minus column. Right. Okay, let me leave you and see if you find the value of x. So find the value of x. You can either use the equation or you can use this gradient, right, to find the value of x. Right. So you can just say x is the number of electrons that give you a charge of, and remember when they give it in graph, you have to look at the unit on the graph. The 2 they gave us was 2 nanocoulombs, right? So you have to convert to coulombs. You have to 10 to the minus 9 to get back to coulombs, right? And then it's just division. If you prefer to write it as gradient, you could have said the gradient is now equal to QE, right? That's what I got in the previous one. How do you get the gradient of that line? It's the final y number divided by the initial y value. So it was 2 times 10 to the minus 9 minus 0 divided by, on the x-axis, x minus 0, and that is 1.6 times 10 to the minus 19. And then you would have ended up with the same thing, x being 1.25 times 10 to the 10 electrons. Right. So then you can use either that one or that one. Sometimes they have you work out the gradient first, and then they tell you use the gradient too. Then you were stuck with this one. All right, next one. Now, guys, this is a little bit about power and about electricity and how you buy electricity. Now, actually, we're going to look at that tomorrow. So I thought maybe we can just skip forward quickly and look at that and then come back. Then you will have this easier. So can you turn right up to page 47? Right, now, usually, what is the unit in which we measure energy? Energy? Joules, huh? Energy in joules, right. But when you buy your electricity from Eskom, they don't tell you so many cents or rands for 1 joule, right? They measure it in what they call units. What's a unit? Kilowatt hours, right? So we've got a problem. It's not... Now we used to do it. We used to say P equals W over delta T, right? We used to have that one in joule, right? And power we measure in watt. And time we measure in seconds. But now if you want to do your electricity bill, then you can't work like this, right? If you want to do your electricity bill, we can't have that in joules because Eskom is talking about kilowatt hours, right? So instead of putting this in watts, we are now going to put it in kilowatts. And instead of putting this in seconds, we are now putting it in hours, right? So then if you say P times delta T, that will be kilowatt times hour, and you will end up with kilowatt hours. That's nice, right? Why do I need that? Because they're going to give us the cost of our electricity by multiplying the energy that is now in kilowatt hours by the tariff that is in rand per kilowatt hours. And then that works out nicely. Right. So we have to convert first and put it in the right units in order to get kilowatt hours. So quickly, do example 1 up there. P equals W divided by delta T. In what should I put in the power? Should now be in kilowatts. So I've got 3,000 watts. That should make 3 kilowatts. Right. And I'm looking for the energy. Time, nice. They already give me as 2 hours. Right. So that gives me 6 kilowatt hours when I multiply that. Right. And then I'm going to say the cost is equal to the energy times the tariff. Right, and the energy being 6 kilowatt hours, right? And they told us that the tariff is 140 rand per kilowatt hour, right? So it's just 6 times 140, and then I hope you end up with 8 rand and 40 cents. Right. Not too expensive, right? Not too expensive. But if you add that up, all the appliances in your home, right? All the days of the month, then that is where Eskom get that power use from. Right. Right, there's another example just there to practice on. Right, so this time I'm going to do the cost first. Cost equals energy times tariff. Right, cost, well, I have a whole 100 rands to spend. Right, I'm looking for the energy, and the tariff was 180 per kilowatt hours. Right, so I'm going to divide, and that will give me 55,6 kilowatt hours of energy that I can buy. And then you go to P equals W over delta T, right? Let's see if I can put this. Right, and now I know the energy is 55,6 kilowatt hours. I'm looking for the time. Right, 800 watt microwave, I have to put it in as kilowatts. So that should be 0,8, right? And then I get the time, and the time is 69,4 watt. Hours, seconds, minutes? Hours. Now it must be hours. Right. In that one, it's always hours. Are you happy? Right, so this is the background. Now we can go back to our question, right? Question was on page 35. Right, a hairdryer has different settings, and now you're using, sometimes you're using it warm, and sometimes you're using it cold, and sometimes you want it to blow fast, and sometimes you want it to blow slow, right? So this girl is using it at a 3 kilowatt, and then she's using it at a 2 kilowatt setting. She's switching it, right? Okay, it has different settings. The graph shows the power of the dryer versus the time. So she's using it at a setting of 3 kilowatts for 2 seconds, and then she's turning it down. I think it was too hot, right? And now she's using it 2 kilowatts for another 4 seconds. Now, the graph shows the power versus the time for the drying process. Use the graph, right? Use the graph. That means I want to see area, or I want to see gradient. Right? Use the graph to calculate the amount of energy. So I'm looking for energy that is used in 6 seconds. Right. Now, what equation do we have with P and delta T and W? Right. I hope you remember that, and P equals W over delta T. Right. Okay. So, gradient will not be much use, right? The gradient 0 and 0. Let's try something else. What is the area under that graph? The area under that graph should be the two axes multiply. So that should be P times delta T. And what is P times delta T? Oh, nice. That gives us the energy. Right. So if they ask us to calculate the energy, I'm going to say, the space is a bit limited. I'm going down there. Oh, sorry. Right. Okay, so I want W, and I'm going to do the area under the graph in order to get that right. But I want to make it more difficult. I want it in kilowatt hours so that I can work out the cost in the next one. Right, so we have to do it in kilowatt hours. Right, so it's the area under the graph. So first I'm going to do that part of the graph. Okay, so that is nice rectangle, so it will be 3, and just remember it is kilowatts, right? What unit should I use? Kilowatts, so it's nice, yeah, 3 kilowatts, right? Times, this is 2 minutes. How do I get it into hours? 2 divided by 60 to make it hours, is that right? Okay, then I get to the next part, that one. Right. How many kilowatts? 2 kilowatts. For what time? 4 minutes. How do I get that to hours? Divide by 60, and then I have it in hours. Right, so you have to have the units right if you're working to kilowatt hours, right? So this gives 0.1 and that gives 0.13, altogether 0.23, and now kilowatt times hours, nicely kilowatt hours, right? Okay, so I know how much energy is being used. Now they ask us, if the price per kilowatt hour is R2.60, calculate the cost for the process. Right, do that one quickly. Right, 61 cents. It doesn't sound a lot, eh? But remember, you have to add all your cell phones and all the lamps and all the computers and all the fridges and all the ovens and things together. So at the end of the month, it's not 61 cents because it was a little bit at a time, but they all added together, right? Okay. Everyone happy? Can we move on from this one? Right. So let's go on. Now, what we've learned today, we are now going to apply to Newton's law of gravity, right? Newton's universal law of gravity. Now, when we did Newton's laws on Monday, remember I told you we're not going to look at that on Monday? Right, because we're now going to look a little bit at this. We're going to apply what we learned today on Newton's universal law. Right, so first thing I want to know is, what is the catch? What is the thing that goes wrong in Newton's universal law? That R, right, that R, right? It's between their centers, right? It's between their centers. So if you are somewhere, right, and you've got the Earth somewhere, what do you have to put into R? R is the distance between the centers, right? So you have to put in that whole center there, right? So if you have to put in that, you have to remember, usually they just give you the height, right? They gave you just that part. And then you have to add the radius of the Earth. And on your information sheet, they give you the radius of the Earth, right? So you have to know when to add and when not to add, right? So that's for that one. Then weight and mass. Tell me, what is mass? Mass is just, right, the measure of the amount of matter. It's your molecules, right? So when does that change? Does your mass change when you go to Mars? No. How do you change your mass? By going on a diet, right? Or doing a lot of strenuous exercise, right? So the only thing that stays constant, and that's the thing I highlighted there for you, the mass is the one variable that stays constant when you go up in the air or even to another planet, right? So your mass doesn't change. You have to be very busy with drastical change if you change mass. You have to go on a diet for a long time, right? So, and then we've already talked about this one, right? Remember, the top one is on the information sheet. The bottom one is not. So you have to derive it when you have to use it, right? So that is the background that we are going to have to use when we look at the questions, number 7. Right. Right, I want you to look at number 7 and see what you can do for me there. Right. Right, what is represented by the gradient of this graph? Right? First, what is the equation that we're using? We're using Fg equals m times g, right? Now you're not on Earth, right? So g is not 9,8, right? We're on another planet X. But still, it should be the same wherever you go on planet X, right? So that one is a constant. So F directly proportional to m, and that's why they have a straight line through the origin. Right, they are directly proportional. But now I'm asking what is represented by the gradient, right? If you get the gradient of that one, the gradient will be the gravitational force divided by m. Now if I have Fg divided by m, what will that be? Well, nice. Gravitational acceleration, right? So this time the gradient is just the acceleration. So you have one of two options. When they ask you to use the graph to calculate it, you can work out the gradient, right? Or if you prefer, you can take that Fg equals m times g and take that value and say, when the m value is 10, then the gravitational force is 49. And you can use it like that, that's well, right. So then you will get G being 4,9, right. So you have your 49 divided by 10, so the gravitational force 4,9 meters per second square, and that will be towards x, hey, towards x. So that is if you want to put it into the equation. Or you could have preferred to say, I now know the gradient is equal to G, right? And how do I work out gradient? Gradient is final y value minus the initial y value divided by final x value minus initial x value. And that would have given you the same, 4.9 meters per second squared, and that will be towards x. Everyone happy? Right. And now they ask you, we now know g is equal to 4,9 meters per second squared. If the radius of this planet is the same as the radius of the Earth, how does the mass of this planet compare to the mass of the Earth? Right, so we're looking at the gradient equation, right? G equals gm over r squared. Right. Now, if they asked us how the g changed, this would have been nice, but they are talking about what? What do they ask about? How does the mass change, right? So rewrite it to get mass in front. If you want mass, what will mass be equal to? Right? Mass should be g times r squared over g. Your math's okay. Right. Right. So this is for the Earth, right? If I wrote it like that for the Earth, right? And now I want to know how the mass of planet X compared to Earth. So let's say mass X. Right. Now, if this was the Earth, what would I have put into G's position? 9,8, right? What am I now going to put in? 4,9. How does that compare? That's half, eh? So half. So the new G is a half the old G. It's G divided by 2, right? Because now we have 4,9. Over there it used to be 9,8. What did they tell us about the radius? Same. So R is just the same. What do you know about big G? It's in the same universe. It's a universal constant, right? So what do I want to remove to get back to the Earth's mass? That half up there, right? If I remove the half, I get back to g r squared over g, and that is the mass of the Earth. So this is now half the mass of the Earth. Right. So remember, there's two equations for weight, right? Two for your gravitational force. You've got for gravitational force, you can use Fg equals mg, but for gravitational force, it's also gmm over r squared, right? They're both talking about your mass, right? Okay, I think our time is a little bit limited. Let's move on to number 7 there at the bottom. Right. 7.7. Planet X has 3 times the mass of the Earth and double the radius. And now they ask us, calculate gravitational acceleration on Z. Now, they're asking us about Z. What do we have to compare with? We always have Earth to compare with, right? The fact that we're living on Earth, tells me that I know the G value on Earth, right? Do you know the G value of any other place in the universe? No, it's not important. We're living on Earth, right? So we know that 9,8, right? So if they want to calculate the gravitational acceleration on Z, I'm going to start off by saying, if you asked G on Earth, that would have been, and I know the value, and an equation for that would have been g m over r squared, and I would have known that was 9,8 meters per second squared. Right. Now I'm going to planet Z. Okay, I am now on Z. Right. What happened to G? Nothing, same universe. Right. What happened to the mass? Well, planet Z has 3 times the mass of the Earth, so that should be 3m, right? And double the radius, 2r. And remember the square, right? So what do we end up with? 3/4 of g on Earth. And that means 3/4 of 9,8. Right, and what is 3/4 of 9,8? hopefully you find that as 7.35 meters per second squared, and that will be towards Z. Right. Right, quickly do number B. Right, gravity is always m times g, right? And we've already calculated g on this planet Z, right? So it's just 10 times that. Right, so remember that's the other way. You don't have to go the long way around. Right. So there's still a few questions that we had to answer at the end of the first day and the second day, right? We didn't do that inclined plane yet, and we haven't done the percentage ones. We just referred to that. We didn't do all the percentage questions, right, yesterday. So tomorrow I want to look at all those little bits and pieces that we left, right? And we're also going to look at electricity, right? And in the Afrikaans class, they asked me to look a little bit at redox. Is there something that you would like to look at tomorrow? What? Acids and bases, a little bit at acids and bases. Okay, it's fine. I'll find out how many you are and just give you some papers, and then we'll talk about it. Sorry? Oxidation and reduction, the half reactions and the total reaction. We'll see tomorrow. I think I'll prepare, and then we can decide if we're doing more electricity, or we'll rather quickly look at acids and bases, and then see how we can put our time to the best use. Is that all right with you? Okay. Right. Then I'll see you tomorrow.